In this lesson, we're going to talk about the water molecule and intermolecular forces. Water, of course, is a very unique substance. It's also the most common substance on our planet, H2O. It bonds in such a way as to form a bent molecule. That molecular shape is important. Also, there's a difference in electronegativity between oxygen and hydrogen, a very large difference. We indicate that with these little squiggles. The squiggle negative means partial negative charge, and the squiggle positive around the hydrogen means squiggle positive charge. It's a polar bond. That doesn't mean that electrons are stolen by the oxygen, but it means that among the shared electrons, they're going to hang out more of their time near the oxygen atom than the hydrogen atom. So we call that any kind of a bond where there's a positive and negative end is a polar bond. And then when you consider the entire molecular shape, whether those, you may have polar bonds that cancel out. Well, in the case of water, they don't cancel out because of the bent shape. And so we say this is a polar molecule in addition to having polar bonds. Let's talk a little bit about density. Water can exist just like anything in any of three commonly found states of matter: solid, liquid, or gas. And of course, gas is the least dense state for anything. And for almost anything, the solid state is the most dense state. But that's not the case for water. Water's solid state is actually less dense than its liquid state. It's extremely unique and extremely important. And we need to talk about that a little bit and some of the properties conveyed to water because of it. Take a look at this. Here's a picture of a scuba diver swimming under ice. Under ice. Just like when you drop an ice cube into a drink, it floats. Well, an ice cube, like an iceberg in the ocean, is going to float to the surface, which means you can swim under it. Why does that happen? Why is the solid state of water less dense than the liquid state? It has to do with how water molecules interact in the solid state. When they're packed closely together, the attraction among adjacent molecules forms what's called a crystal lattice structure. That crystal lattice structure has holes in the middle of it, and the holes in the middle of it decreases the density. And if you have a lot of it, which of course you would if it's a big piece of ice, you have a lot of holes in the structure. And as a result, it's enough to make solid ice less dense than liquid water. So it's startling fact. Other unique properties of water. Pictured here is a bug called a water strider that actually, literally and non-miraculously walks on water. And the way it does that is it pushes down on the surface of the water. If its legs were, if the force of gravity on its legs were exceeded that of the attraction between adjacent water molecules, it would push through the surface and it would have to swim in order to go on the water. But the water strider, number one, it's really light. It's a small bug. Number two, it's got huge feet for the size of its body, which helps to distribute its mass. And then thirdly, of course, is the water itself. The water molecules on the surface of the water adhere to each other more strongly than the gravitational attraction of the bug towards the center of the earth, that is, to pull it downwards. So water has a really high surface tension. Here's a plot of boiling point versus hydrogen substances bonded to group 16 elements. So if you look on the periodic table, group 16 has oxygen, it has sulfur, it has selenium, and it has tellurium, all of which would bind to hydrogen in the ratio 2 hydrogens to 1 of the group 16 elements. If you were to plot boiling points, the general trend, let's ignore the water here, the general trend is that the higher the mass of that molecule, the higher the boiling point. So if that were the trend, we would expect water to have a boiling point somewhere around -90 degrees Celsius. But instead, we see something very different. H2O's boiling point is at a positive 100 degrees Celsius. That tells you something about the strength with which the liquid molecules adhere to each other. Because to boil means to move from the liquid state to the gaseous state, to move from a state where molecules are touching each other to a state where they're not. And to make that move, you've got to actually pull the molecules apart from each other. The energy that is required to do that is proportional to the boiling point. And since water has really high intermolecular attraction between molecules, it's got a wicked high boiling point for its molar mass. It's a very shocking trend. Other things unique to water, it's known as the universal solvent, meaning it can dissolve just about anything. And pictured here, you'll see both a negative ion being attracted to water. It's particularly the hydrogen side of water is attracted to the negative ion, and a positive ion being attracted to the other end, the oxygen end of water. Water can attract both and dissolve them. Water has a high specific heat capacity. Now, that's something we'll visit when we study thermochemistry. It means it takes a lot of energy to raise or to lower its temperature. There are many cities along the coastline that have moderate climates, even despite their high latitude, as a result of water's high specific heat capacity. Take Seattle, for instance. Seattle is further north than Chicago. And by virtue of its latitude, you would expect Seattle to have more severe winters than Chicago does. But Seattle is close to the Pacific Ocean, close enough. In fact, it's right on an inlet of the Pacific Ocean called Puget Sound. And that's close enough that the Pacific Ocean's climate moderating effects make Seattle's winters much more mild than Chicago's, even though we're further south. So it's really rare for it to snow in Seattle, whereas it's not so rare in Chicago. Water also has a high heat of vaporization. That's another way of saying it takes a lot of energy to make it boil. We saw that graph of boiling point just a moment ago, which illustrated the high heat of vaporization. These amazing properties can all be explained by the attraction of water molecules to each other. Now, let's make a really important distinction. Take a look at this chart or picture here. Water consists of 2 hydrogens and 1 oxygen bonded together covalently. Those bonds within the molecule, shown by the purple lines within the purple blobs, are intramolecular forces. Intra means within. The other kind of force, illustrated in the pink lines that connect the purple blobs one to the other, are intermolecular forces. Inter is a root that means between, and intra is a root that means within. Water's amazing properties can be explained by its uniquely strong intermolecular forces. Even though the intermolecular forces are always going to be less strong than the intramolecular forces, water still has very strong, among a comparison of other molecules, very strong intermolecular forces, and that's why it behaves the way it does. Let's talk about 3 types of intermolecular forces. The first one is called dipole-dipole attraction. This consists of an attraction between the positive end of one molecule and the negative end of another. Take a look at the 2 hydrochloric acid molecules pictured here. The squiggle positive around the hydrogen indicates partial positive charge. The squiggle negative near the chlorine indicates partial negative charge. By the way, the squiggles are the Greek letter delta in lowercase form. It's what chemists use to indicate partial charge. Notice that one HCl molecule experiences an attraction to the next HCl molecule over. Specifically, the hydrogen end of one molecule attracts the chlorine end of another. anytime you have a polar molecule, a molecule where there's a positive end and a negative end, the positive ends of one molecule will attract the negative ends of another, and those momentary brief attractions do add up and cause things like higher than usual boiling points and other kinds of properties that water has especially strongly. Okay, so dipole-dipole is one type of attraction. And to consider that, we have to think about, or remember, electronegativity. Electronegativity, if you recall, is the ability of an atom to attract shared electrons. So automatically, we're ruling out noble gases because noble gases don't typically participate in bonding. If we graph electronegativities among the other elements, generally you're seeing the highest electronegativities in the upper right corner, with fluorine being the highest, followed by oxygen, followed by nitrogen, which is a tie with chlorine. They're all on a ranking with 4 being the highest. So 4, 3.5, 3.0, and 3.0. Everything else is something less than that. And so I would invite you to remember these ones, F, O, N, and Cl. Those are the most electronegative elements out there. Funkel is a way to remember those three. Which brings us to type 2 of the intermolecular forces, hydrogen bonding. Hydrogen bonding is of the same nature as the dipole-dipole attraction, polar molecules attracting each other. But there's a specific case. We need a specifically hydrogen bonded to one of those extremely electronegative elements, fluorine, oxygen, or nitrogen. And I mentioned chlorine as one of those, but if you just think of F, O, and N, phone, bonded to hydrogen, if that's the case in any molecule you're considering, like water, hydrogen bonded directly to oxygen, then the molecule will experience hydrogen bonding. Why? You might say, okay, I get that you have a really electronegative element bonded to something that's kind of a medium electronegativity, hydrogen, but why is that so important? Hydrogen is really small. The size of the hydrogen atom is the smallest of all of them. And so the result is the adjacent molecules, let's say we got several water molecules in a collection, the water molecules can get closer together because the hydrogen that would keep them spaced apart is small. So there's a close approach in addition to a great electronegativity difference within the bonds. This type of bond, intermolecular force, is what gives water its very unique properties. This is the key one, and it's the strongest of the intermolecular forces. There's one more that I'd like to mention. They call it London dispersion forces, sometimes also called van der Waals forces. This consists of a weak attraction between molecules with instantaneous dipoles. Instantaneous meaning short-lived. So it's weak and short-lived. But it's the only kind of intermolecular force that non-polar molecules can experience. So we've got dipole-dipole limited to polar molecules. We've got hydrogen bonding limited to polar molecules, and specifically ones that have hydrogen bonded directly to fluorine, oxygen, or nitrogen. And then the third type of intermolecular force, London dispersion forces, everybody participates in. Within the London dispersion force world, the trend is the bigger the molecule, the greater the London forces. Let me show you a picture of how this works. Here's a picture of two atoms, atom A and B, and let's say they're pretty big. These atoms have lots and lots of electrons. Let's say each of these dots represents an electron. So we're talking like 100 electrons. This might be like Einsteinium, which is element number 99, which to be neutral would need 99 electrons in it. Okay, so if it's a neutral Einsteinium atom, the electrons might temporarily be moving in their random way around the nucleus, they might be moved to one side over the other. They're not necessarily always going to be an even distribution. And if atom A, just momentarily for a fraction of a second, has more electrons on the left side of its nucleus than on the right side, that would induce an attraction for the atom B next to it, its electrons to slosh towards the dearth of electrons on the right side of atom A, because here's a partial positive charge, and well, partial positive charges attract partial negative charges in the adjacent atom over. Even though after a fraction of a second, the electrons might redistribute and more evenly space themselves out, that short attraction does add up, and it matters. Okay, this attraction lasts only for a fraction of a second, but all molecules can participate in it. Let's rank the strength of the forces we've been talking about. First, I want to underscore that by far, regardless of what type of intermolecular force we're talking about, the strongest force is the force within a molecule, an intramolecular force. So the bond between oxygen and hydrogen within the water molecule is way, way, way stronger than the hydrogen bonds that are between water molecules. Nevertheless, those forces between molecules are still very, very important. And if we were to rank them, we'd go like this: hydrogen bonding, the especially strong dipole-dipole force, followed by normal dipole-dipole forces, followed by the weak instantaneous London dispersion forces. Keep in mind that ranking as we assess different molecules. I'm going to jump down one moment here. Jump down to a sample problem. Let's say we're asked to consider which types of intermolecular forces would the following molecules exhibit, and then rank the strength of their intermolecular forces. Okay, CH4, NH3, and CO2. I want you to consider the differences in electronegativity between the bonding atoms. So C and H within CH4 have very similar electronegativity values. That is, the C to H bond in CH4 is nonpolar. There's an equal attraction to the shared electrons between the carbons and the hydrogens. And I know that by looking at the chart, the electronegativity chart, or you could just remember on the periodic table, if it's not fluorine, oxygen, nitrogen, or chlorine, then it's not a particularly electronegative atom. Okay, so we've got a nonpolar molecule here. The only kind of intermolecular force that CH4 would exhibit is London dispersion forces. How about NH3? In NH3, we have one of those three extremely electronegative elements, nitrogen, bonded directly to hydrogen. That's the recipe for hydrogen bonding. So NH3 participates in hydrogen bonding. It also then necessarily, because of the polar N to H bond, would participate in dipole-dipole attractions, and everything, including nonpolar molecules, but this one's polar, everything participates in London dispersion forces. So all three types of intermolecular forces are at play in NH3. Next, let's look at CO2, carbon and oxygen. We have a very electronegative oxygen atom. F, O, N, and Cl are the very most electronegative elements that I want you to remember. And it's bonded to carbon. Okay, so it's a polar bond. Now, in thinking about the shape of CO2, we have to consider molecular shape. It turns out, if you were to draw a Lewis structure of CO2, it's linear. That is, the two bonds that make it up are exactly 180 degrees apart. Let me show a picture of the molecular shape of these three molecules. So CH4, we said, is nonpolar in each of the bonds, and there's 4 of them oriented exactly as far apart as they can be from each other in space. In NH3, we have polar bonds, and the 3 of them are oriented as far apart as they can be, but there's this lone pair of electrons that pushes those 3 N to H bonds all downwards. So the NH3 molecule has a molecular dipole. It is a polar molecule overall. CO2 consists of 2 bonds oriented 180 degrees apart. And even though the individual bonds are polar, the fact that they're oriented exactly opposite each other means that the bond dipoles cancel out and you have a nonpolar molecule overall. So the types of intermolecular forces that CO2 can participate in would only be London forces. Oh my. So 2 of our molecules only participate in London forces, and 1 of them participates in hydrogen bonding, dipole-dipole, and London forces. By far, NH3 has the greatest intermolecular attractions. Thanks for your good work.